All right, so finding a definite integral, finding a piece of area could be as easy as just using geometry to find that. Unfortunately, most curves, sine, x squared, e to the x, most of them are not lines and half circles. So that's pretty limiting, number one. So then the next step would be to just approximate, count squares, kind of count squares. Or we even did a thing where we put little trapezoids underneath the curve and estimated, right? We did like 4 of them or 10 of them, and we estimated. We said, well, that's pretty close, and we could get an estimate that way, an approximation that way. But it'd be better if we could get an exact answer. And so then we went through all that stuff with the area function and the fundamental theorem of calculus and all that cool stuff that we made. We figured out that, hey, the antiderivative somehow is connected to area. And sure enough, we came up with this fundamental theorem part 2. Do the antiderivative of whatever this function is here. Plug in a b, plug in an a, subtract them, and voila, you got the area. That's pretty cool. So this is a big deal. So therefore, if this is going to work, we got to be able to do the antiderivative. So our goal in the next week is to try to be able to do the antiderivative of as many different functions as we can. Now, a word of caution as we go into this. Derivatives, we can do the derivative about anything. Now, it might be undefined some places, but we can take any function, divide it, multiply it, put it inside of itself multiple times. We can find the derivative. We have a list of rules, and we can do it. Antiderivative is not going to work quite the same way. There are a lot of functions out there that do not have an antiderivative. Matter of fact, I'll just show you one right now. I can make them up all day long. It's pretty easy. This function right here does not have an antiderivative. It just doesn't. Why not? Well, what do you need for something to be an antiderivative? What would the answer, if there was an antiderivative to this, how would we check it? Do the derivative. So to have an antiderivative means there has to be, the answer would be a function that when you did its derivative would get you back the sine of x squared. And guess what? There is no function that when you do its derivative will give you sine of x squared. It just won't. There isn't one. And there's a lot of them like that. Okay? So when you look at your list of how we're going to do areas, as great as fundamental theorem part 2 is, it only works when you're able to find an antiderivative. If you can't find an antiderivative of this function, there's still an area. If I graph sine of x squared and I wanted to look from 0 to pi, there'd be an area. But since I can't do the antiderivative of this, I can't use fundamental theorem part 2. So approximation, even though it seems like, why would you put that in there? Because that seems like a dumb thing to do when you could get the exact answer. Well, guess what? Sometimes you can't get the exact answer. So that's what chapter 6 is about. What happens when we can't do an antiderivative? Oh, we have to do an approximation. So we're going to talk about how we do approximations when this won't work. Okay? All right. But that's getting ahead of ourselves a little bit. For right now, our focus is going to be what about functions where we can do the antiderivative? And on the gateway test, you'll be able to do the antiderivative. There's not going to be any, that's not going to be an option for you to say, oh, you can't. You're not going to have to figure out if you can or can't do the antiderivative, right? I'm only going to give you ones where there is an antiderivative. Okay? All right. So, here's 3 different integrals. Let's write down here. Let's talk about what we have learned so far about integrals. What have they looked like? There's basically been 3 types of integrals that we have been talking about. The first one is this one. This is just a definite integral, right? This is our run-of-the-mill, what we were just talking about. This is your basic, right, fixed piece of area. And fundamental theorem part 2 would work quite nicely on this, right? So we would do the antiderivative, right? What's the antiderivative of x squared? 1/3 x cubed. The power rule for antiderivative says we raise the power up 1, divide by the new power. So 1/3 x cubed. Remember our right bracket notation? right? Now on the gateway test, we're going to do some definite integrals where we actually have to find the area. And then there's going to be a lot of them where all I want you to do is the antiderivative. Just do the antiderivative and stop. Okay? Like we did on the derivative gateway test. Just do the derivative and stop. Right? So, but let's go ahead and finish this one. Let's go ahead and put our 4 in here. What's 4 cubed? 64. So that'd be 64 thirds minus, and then 3 cubed, 27 thirds. So 64 thirds minus 27 thirds would be 37 thirds, I think. Right? 37 thirds, 12 and 1/3. Just a number answer. That's it. Okay, so we have those kind of integrals. Definite integrals where we do that. Now, what about this next one? What is this? When we have this x up here. Well, what do we call that? Yeah, area function. It's an actual function now, right? Where we slide the right endpoint, right, back and forth. So our answer here is not a number. Our answer here is not a fixed piece of area, right? It's actually a function, right? It's a function. Now, there are 2 ways we could find this function. There are 2 ways we could find this function. Matter of fact, this would be good review right now to do that. So here's the one way we did it. Is we knew that the area function means, I know it's been a weekend, you didn't have any homework, but area function means antiderivative, right? When you see this, that means antiderivative, right? That was all the big deal, fundamental theorem part 1. Area function means antiderivative. What's the and we have to put t in here because we're using x for this. What's the antiderivative of this? 1/3 x cubed, right? Plus c, right? So it'd be 1/3 x cubed plus c would be our function. But how can we find the c? Let's pretend that this was called big F. We know that big F of 3 is 0. Remember that? So that means we can plug a 3 into this, so we could get 1/3 times 3 cubed, and we know, plus c, and we know that would equal 0. Well, 3 cubed is 27. 27 times 1/3 is 9. 9 plus c equals 0, so c equals -9. So we know that this function is 1/3 x cubed minus 9, right? It's a function. It's the area function. That's it. Notice up here in number 1, when we do a definite integral, it is a number answer. It's a fixed piece of area. When we do it here, it's a function. It's the antiderivative with some c tacked on that we can find. Now, there'd be another way we could do this. We can actually use fundamental theorem part 2 here. It's kind of a slick way to do it, to be honest with you. You could do this the same way we did this up here. I can say to myself, what's the antiderivative of t squared? Well, that'd be 1/3 t cubed. Now, you might be saying, why'd you leave the t in here? Well, you'll see here in a minute. And I could have done my right bracket notation. I like this, too, because this also points out why your final answer ends up having x in it instead of t. I could have done the antiderivative of this, which is 1/3 t cubed, and put a 3 and put an x right on there like that. Right? And now just do fundamental theorem part 2. So plug the top number in, which is x, so I get 1/3 x cubed, minus, and now put 3 in there. I get 1/3 times 3 cubed. Well, what's 1/3 times 3 cubed? 9. And look what I get. 1/3 x cubed minus 9. That's almost a little easier than doing what we had done the other way. So when you get one of these area function things, you can do this. Right? You can do the antiderivative of that, plug in x, plug in 3, and sure enough, when you plug in that 3, it gives you the c. And then didn't we know that the 3 was the c, right? I mean, the 3, that left edge, is what determined the c. All right, now, let's go to this last one. What's the only difference between this one and this one? We don't know what the left edge is. It could be anything. Well, what's that mean then for our area function? What would be different in our final answer? We wouldn't know the minus 9. It would just be 1/3 x cubed plus, well, if we did it this way, it'd be 1/3 x cubed minus 1/3 a cubed, right? But what's a? Just some constant. So what's 1/3 a cubed? Some constant, it's just the plus c, right? I mean, so there's no reason to write it with an a. There's no reason, let's just write it like this. In other words, we don't know what the left edge is, so it's just our plus c. So the difference between these two here is this one is a specific antiderivative, when we know our left endpoint, and this one is the general antiderivative, right? When we don't know our left endpoint, and we just get the antiderivative plus a c. This last one is what we're going to be doing mostly on our gateway test. So here's the thing. If I don't know the left edge, and I don't know the right edge, right, because it can move, then why even write them on there? So that is called an indefinite integral then. So so number 3 down there, where we didn't know the a and didn't know the x, why write an a and an x on there if they're both unknown things? Let's just write an integral symbol with nothing on it, and that tells us we're looking at an antiderivative. On your calculator, and you can use your calculator just to check, but all this week the emphasis is going to be no calculator because our gateway test is no calculator. But on your calculator, there's an integral symbol with the boxes for the a and the b. That's when you're wanting to do a definite integral. And then there's an integral symbol with no boxes, and that's when you're wanting it to do the antiderivative. So somebody in the other class was asking, do our calculator, will our calculator do antiderivatives? Yeah. Do the integral symbol without the boxes. So if you type in the integral symbol and if you type this in right here, okay, you should get 1/3 x cubed. And I don't mind you doing that because, I think it's x cubed over 3. We'll probably do it. Now, does it put on the plus c? It does not. You have to remember to do that yourself. All right, so this integral symbol, without anything on it, is called an indefinite integral. And what that is saying is, hey, do the antiderivative. That's what that's saying. Do the antiderivative. Okay? Now, when I was in college, or in high school too, I never understood, until I started teaching, that integral and antiderivative are two different things. I always thought they were just the same thing. Antiderivative is just one way of finding an integral. Right? It goes back to my first string. Antiderivative is just one way of finding a definite integral. Okay? But when I was in school, we learned this first, and then we got into areas and all that stuff. And I like how your book does it. And I always thought integral just meant antiderivative. It doesn't. Antiderivative is one way of finding integrals. It's a big way. It's the most useful way. All right. So there you go. So you can use your calculator to check as you're going through these and so forth, just like you did when you did derivatives. All right, what's the antiderivative of sine? Negative cosine. Now we're about ready to start getting into here how we're going to do antiderivatives. Now, the first way, of course, is just your basic antiderivatives. It's the derivative rules in reverse. Okay? So, and sine and cosine is always a tricky one. The way I remember it is I always remember the derivative of sine is cosine, and then everything falls from that. Derivative of sine is cosine. So therefore, the antiderivative would go backwards. So the antiderivative of cosine is sine. Then the other one is the negatives. The derivative of cosine is negative sine. So the antiderivative of sine has to be negative cosine, right? And of course, you can always just do your derivative and check, right? You say, hey, I think it's cosine. What's a derivative cosine? Negative sign. Oh, no. Okay, I got to have a negative, right? So, I mean, you can always do the derivative to check your answers on these. All right, so this is what we're going to be doing. Now, we'll mix in a few definite integrals, too. So you'll have a few like this where you have to do the antiderivative, right bracket, and plug in your numbers. But mostly, we're just working on this. All right, now look at page 333. All right, page 333, we need to know, this is what you have to learn. Remember we had that whole big page of rules for derivative formulas? This is it, right here. Now, there's some other techniques, we'll call them, not rules, but techniques for doing this. But basically, what we will learn is a bunch of techniques to make every integral we run into look like page 333. That's our challenge this week, is to make every derivative or every integral we have, to do algebra to it and to use some techniques to make it look like page 333. So we need to know the power rule. If you have integral of a power, you raise the power up 1, divide by power. That's the first one on that page. The second one, we have to know that the absolute value, or excuse me, the integral of 1 over x is natural log of x. But notice there's bars around it. You have to put that. Here's why. Because natural log cannot accept a negative input. And if you have an integral of 1 over x, x could be negative. There's nothing telling you x can't be negative. X can't be 0 if you have 1 over x. Now you might say, well, why didn't we do that when we did the derivative? Right? If I give you this problem right here, derivative of ln x, and you were supposed to do that, and the answer is 1 over x, we didn't put bars around anything. Why not? Why didn't we put bars around this? Well, there's no need. Can x be negative in this problem? Can x be negative in this problem? No, because the log graph cannot accept negative inputs. So when they gave me the problem like this, I knew x had to be positive to start the problem. However, if I go the other way, if I start with this as my problem, can x be positive here? Can x be negative here? Sure. Can x be 0? No. But x could be positive or negative. When I do the antiderivative, when I do the antiderivative and get ln x plus c, this is not good enough. Because x could be negative, and we cannot allow a negative number to go into natural log. So we need to put bars around it when we do that. So you just have to memorize that. The antiderivative of 1 over x is natural log of x plus c, but bars around the x. Okay, e to the x is its own antiderivative. That's a good one, an easy one. A to the x, and we're going to have to remember that. 2 to the x, remember, 2 to the x, when we did a derivative, would kick out a ln2. Well, when we do the antiderivative, it would be a 1 over ln2. Okay? Notice there's no logs in this one. There's no antiderivative of logs that we have to memorize. Okay? If we run into logs, there'll be a way we'll deal with it, but it won't be a memorization thing. Okay? Of course, sine and cosine are in there. Secant squared, we're going to memorize that one. We should, because we know the derivative of tangent is secant squared, so the antiderivative of secant squared has got to be tangent. And then we got the arcsine and the arctangent, which we'd already talked about those. Now, I don't like it when they put that dx up on top. And maybe somebody wrote that in your book already. I would put a 1, I would rather see a 1 over square root of 1 minus x squared, and then the dx off to the right. Because that's how we're always used to seeing it. That's how I'll always write. But in the book, sometimes they don't. Okay? So I don't like when they put that dx up on top. It should be out to the right, put a 1 up on top. All right, you need to memorize page 333, those antiderivatives. All right, now, let's do this problem right here. Okay? So here'd be an example of what I mean. So, remember we had the rule about splitting up our integrals? Right? And we can pull things out in front. Well, sometimes that's a good idea to do. Now, I wouldn't do it here. I wouldn't write this as 3 separate or 4 separate integrals, but you could. Right? And then each one of these would look like page 333 with a couple of little minor things that we might have to take into account. So, for example, let's do this first one. What's the antiderivative of 3x to the 4th? 3/5 x to the 5th, because it's a power rule. We raise the power up to a 5, and we divide by a 5. The 3 just hangs out there, right? I could split it. I could pull it out in front. No need to. Just hang out there with it. Okay, you got that. What's the antiderivative of e to the 3x? Now, I'm going to show you something today of how we can handle that 3. But if you can do this in your head, it'll be a lot better. What's going to happen with that 3? We're going to have to kick out a, Riley, say it louder. We're going to have to kick out a 1/3. Remember when we did the derivative, we would kick out a 3? Remember that? Think of it this way. If you're thinking to yourself, hey, the antiderivative of e to the 3x is e to the 3x, let's check it by doing the derivative. Well, the derivative would be 3e to the 3x. Oh, that's not what we have. What happened to that 3? There must have been something sitting there that canceled it out. Remember when we did that? We did some of that. We talked about when we're doing the derivative, we got to kick out a 3. If we're doing the antiderivative, better do the reverse, kick out a 1/3, because if there's a 1/3 sitting there, now when I do the derivative, I kick out the 3, they'll cancel. So this would be 1/3 e to the 3x. So if you can deal with that, especially when you got a sine or a cosine, like a 2x in there, or a 3, if you just know you're going to kick out a 1/2 or kick out a 1/3, we're going to learn a technique today for how to deal with stuff on the inside. But on these easy ones with just numbers on the inside, it'd be best if you just do that. All right, what about 1 over x plus 3? Natural log of bars of x plus 3. Because all that plus 3 is a shift, okay? And think about it. Let's check it with our derivative. The derivative of ln of x plus 3 would be 1 over x plus 3 times the derivative of the inside. Derivative inside is just 1. So sure enough, that's what it would be. So what I want you to see on this problem is how these all look like page 333, but you can have some little bitty changes that you have to deal with, like the 3 on the inside or a shift, right? That kind of thing. All right. And then minus, and then what's this last one? This last one is arctangent of x. And then don't forget a plus c all at the end. Okay? So the easiest, so when it comes to the gateway, the easiest of the problems will be ones like these, where it's just right off of page 333, where you just have to do a straight antiderivative, maybe with a little adjustment with the 3 or the plus or whatever, but it's basically that. Just straight antiderivatives from the list on page 333. All right. So that's kind of basic antiderivatives. Actually, to be honest, before today, we could have done this anyway, right? Because we kind of been doing it. We just haven't focused on it, but we've kind of talked about it, had some examples where we did. There's your antiderivative. Now notice the integral symbol is gone, because the integral symbol is just saying do the antiderivative, and the dx is just saying with respect to x. So when we do the antiderivative, those go away, and we just have this. Just like here when it said d dx ln x, when we did our derivative, it's just 1 over x. The d dx all went away because it was just telling us do the derivative. All right, let's go to this one. Now, notice what I've started with here. Our focus today now, for the rest of the time, is going to be what happens when we got these things on the inside that aren't just like a 2 or a 3. What if we have functions inside? Aaron, on the homework sheet, the next 2 lines down, basically, on the, underneath the quiz. All right, now, so the video will be up if you need it to finalize this. Okay, let's do the derivative first, because remember, antiderivative is just backwards. So let's do this. So what is the sine? What's the derivative of sine of x cubed? No. 3x squared cosine x cubed. Right? Isn't that the derivative? Be the derivative of the outside, which is cosine, leave the inside alone, times the derivative of the inside, 3x squared. So doesn't that mean then that the antiderivative of 3x squared cosine x cubed dx, doesn't that mean that that should equal what? What's the antiderivative of that? sine of x cubed plus c, right? Our job today, with the time we have left, our job today is to say how in the world, pretend this wasn't up here now, right? How in the world could we start with this and know we would end up with that? You see the difficulty with antiderivatives? Because with derivatives, we just follow the rule. With derivatives, if you had things multiplied, we just had this thing called the product rule, and we just did it. We just followed the rule. With antiderivatives, they sometimes say it's more of an art than a science, right? We have to be able to look at this and think kind of in reverse a little bit, okay? Now, the way of thinking of it would be, oh, okay, this has got something on the inside. So when I do the derivative, of course, the inside always stays the same, right? So when you do an antiderivative, the inside is going to stay the same. So this x cubed is going to be in there, but I know when I do a derivative, I'm going to have to kick out a, what? 3x squared. I'm going to have to kick out the derivative of the inside, 3x squared. So what that means is this is a good thing that this is sitting here, right? It's a good thing that 3x squared is sitting here because I need that to be there when I do the derivative. So therefore, it's just really this. Well, that gets hard to think about. I mean, and what if there wasn't a 3, but there wasn't x squared, blah, blah, blah. It gets tough. So here's how this is going to look. Here's how we're going to approach this. This is called U substitution. Okay? So everybody start with this right here. And what we're about to embark on is called U substitution. Our goal with U substitution is to make our integrals look like page 333. It's really chain rule in reverse is what it is. Chain rule in reverse. All right, so what we will learn over the course of the next few days, and even into the rest of the week too, we got some other techniques to learn too, but this is the main one. U substitution is the main one. We will learn what do we want our U to be, because that's what we're going to do. We're going to substitute U's for the X's. Well, the number one thing we want U to be is the inside. That's usually where we focus. Because remember, this is for chain rule problems, which means there's going to be something on the inside. So what we would do in this problem is we would let, and I'm going to write it right underneath, we would start by letting U equal x cubed. We're going to make that substitution right there. We're going to let U equal x cubed. Now, to complete our substitution, we need U prime. But I'm not going to write U prime. I'm going to write du over dx. Okay, instead of U prime. You'll see why here in a minute. Now, what is du over dx in this problem? What's the derivative of U with respect to x? 3x, yeah, 3x squared, right. Yep. This is U, x cubed, so the derivative of U with respect to x is 3x squared, right? Now, I'm going to do something here. You're not going to know quite why I'm going to do it, but we do it every single time we do this, and that is we move the dx over to this side here. We can do that. We can multiply that over there. There's a whole mathematical line of reasoning why we can split that apart, but don't worry about it right now. It's called the study of differentials, but we're just going to know we can do that. Matter of fact, from now on, I'm not even going to do that step. Because we do the same thing every time. When we pick our U, we do the derivative, du over dx, and then we move the dx over there. So since we do it every time, I'm just going to jump right to this step. I'm going to think of du as derivative of U, and so I'm going to say, okay, I'm going to do the derivative of U, that's du, and then the derivative of this side would be 3x squared, and then dx. We tack the dx there. Now, why is the dx there? Because it came from over here. Okay, now if that bothers you, do this middle step every time. That's fine. I just get tired of writing it every single time. I'm just going to skip that step. I'm going to go right to this. But now we can do substitution. Okay, so when I do these problems, I usually write this below. Then I draw myself an arrow over to here. And I'm going to write myself a new integral. But now this integral is going to have u's in it instead of x's. Now, we're doing substitution. So think of it like being a basketball coach. I always think of this as basketball. If I put 2 players in, I got to have 2 players come out. If I put 3 players in, I got to have 3 players come out. Okay? So think of the u's as the second 5. So if I put the second 5 in, I got to take all the starters out. So x's are like the starters, right? That's what we started with, and the u's are like the second 5. So all the starters got to come out. All the x's got to come out, including the dx. That's why we can't forget about it down here. So I like to do a lot of circling. So in this problem, what is the equivalent of cosine x cubed? Cosine of u, right? So cosine of x cubed is, I'm going to circle it. That means I've taken it out, right? Cosine of x cubed is out. It's now cosine of u. Now, what about the stuff that's left? What about the 3x squared dx? What about 3x squared dx? That's du. So I'm going to take out the 3x squared dx and replace it with du. Look what I just did. I just turned this complicated, messy integral into a very simple integral with substitution. Right? It's equivalent. Now, does this look like something on page 333? Absolutely. So what is the antiderivative of cosine u du? Remember, the du just means with respect to u. That's why we couldn't leave a dx there, right? We can't do it u's and then have x's in there. What's the antiderivative of cosine? This would be sine of u plus c. Now, the integral symbol's gone now, right? Because the integral symbol means do the antiderivative. So I just did the integral symbol's still there before, because all I would do is substitute, making a new integral. But now I'm doing the antiderivative, so I got sine of u plus c, and then the last step is substitute the starters back in. So take out the u and put in x cubed. And isn't that slick? There it is, right there. And I could check it by doing the derivative of that if I want. And sure enough, I would get it. And that's how we do it. So, if at first blush, you look at this integral and say, God, that's really confusing because that 3x squared there. No, it's great that that 3x squared is there. Because I needed it as part of my substitution. It was the derivative of the inside. I needed that to be sitting there. I needed that to be sitting there. All right, let's do this problem. Now, normally I would say to you that you should not use u substitution on this problem. This is one we just talked about. What's going to happen with that 5? What's going to kick out? A 1/5, right? But let me show you how you could use u substitution, but I also want you to see that, guys, that's a lot of work when I could just kick out a 1/5. So I'm going to pick my u. What should I use for my u? 5x, right? The inside thing. Okay? So what's my du? My du is the derivative of the u. 5, and then we got to put on the dx. Now, why was that? Because du over dx was 5, and then we swing the dx over to that side, right? But we just do that every time. Just remember du, and then the other side you have a dx at the end when you do the derivative, okay? Now, new integral over here is going to be cosine of u. Are you with me? That's cosine of u, and the only thing I have to take out, is dx. What is dx equal to? I need to move this 5 out of here, right? And which is perfectly legal to do. I need to move this 5 over here. It's 1/5. Let's don't do du over 5. I like the du and dx to be by themselves. Let's make it 1/5 du, and over here we get dx. So dx. So when I take out dx, it gets replaced by 1/5. Now remember how we said we could put the constants out in front? So let's put the 1/5 out there, but the du always goes back here, right? When we put them back in, let's put them back into kind of their normal places. The 1/5 du, I could put 1/5 du out here, but why? 1/5 is a constant. We usually want it out there. Du, we always want at the far end on the right. And sure enough, what's the antiderivative cosine? Sine of u plus c, and then put the starters back in. So take u out and put 5x back in, and sure enough, we get 1/5 sine 5x plus c. But see how that's a lot of work? It's really not necessary. I think it would just be a lot easier if you just know, hey, there's a 5 there, I'm going to kick that out. But with the other one, with the 3x squared, when there's messy x's and stuff inside, then you're better off going through the u substitution. Okay? But we could do u substitution with that. But basically, you see why it ends up being a 1/5, because we had to move that 5 over. All right, let's just keep doing a few more until we run out of time, and then you can go with your homework. Okay? Because we got to practice a few. So here's another one. Now, one of the things we talked about, you guys had a problem in the LH packet when we were getting ready for our last quiz, where we had something over square root of x, and we had to split it apart and subtract powers. And sometimes you can do some algebra simplifying first, and then you don't have to do this stuff. You just get to page 333. So we'll be talking about that this week. Sometimes we can do some algebraic simplifying, but you can't here. You cannot distribute this x into there, right? Can't do it. So we're going to do u substitution. Okay, what do you suppose we're going to let the u equal? The inside. 1 plus x squared. That's exactly what we're going to let the u equal. Now, the first few problems in your homework, they're going to tell you what to let u equal. But then that's the last time that happens. From then on, you're on your own, right? You've got to figure out what you want u to equal. So we're going to let u equal 1 plus x squared. So the next step is the du. Remember, it's du over dx, really, but then we're going to swing the dx over to the other side. So what's a derivative of 1 plus x squared? 2x, and then don't forget there'll be a dx there, right? Because it was over here, and then we multiplied it over there. Okay? All right. New integral. This is by far the most useful antiderivative technique, because chain rule is the most common derivative rule. We almost always have functions inside of other functions. And so u substitution is, on a 10 that we have on the gateway test, there's probably 2 or 3 that are going to be just straight basic antiderivatives where they don't need a technique. And then the other 6 or 7 or 8 that are left, probably 5 or 6 of those will be u substitution. And then the others will be some techniques we're going to talk about here later in the week. All right, so our new integral. Let's start with the big one here, which is where we did our u substitution. What is that? That's square root of u, but I probably should write it what? U to the 1/2, right? So that's u to the 1/2, square root of u. So that whole thing, I like circling it because it just reminds me that I better have everything circled when I get done here. I got to substitute everything out. All the starters are coming out. So I've still got an x and a dx in there. Now I look down here. Do I have an x and a dx here? I do. That 2's in the way, though. Move it over. So let's divide by 2. So that's 1/2 du over here is equal to x dx. So sometimes you have to massage this over here a little bit, right? You got to do something with it. Massage that? Is that? Yes, that's a weird way of saying it, but yeah, that's it. You got to change it a little. Okay, move some things around. All right. So x dx. So there it is. X dx can be replaced with a 1/2 du. Where should I put the 1/2? Out front. The du, clear to the right. So look what I did. I took everything out of this one and turned it into this one. Now, does this look like page 333? Is this an easy antiderivative to do? Isn't it? Which one is it on that page? It's the first one. It's power rule. It's power rule. So we're going to have the 1/2 out here. We're going to bump this up to bump this power up to 3/2, and divide by 3/2. Well, what do you get when you divide by 3/2? 2/3. So this would be 2/3 u to the 3/2, and then plus c. Now remember, I had that 1/2 sitting out there. And we could say, well, you got to take the 1/2 times the c, but that's just still a constant, so it doesn't matter. And what happens here? Those 2's cancel, so it ends up being 1/3 u to the 3/2 plus c. Oh, I should have substituted. Now I got to put my starters back in. So now it's 1/3, and instead of u, I'll put 1 plus x squared to the 3/2 plus c. Now I know Mrs. Andreessen, she wouldn't like this because, you know, the old rule in algebra is if you start with radical notation, your answer probably should end with radical notation. Probably should go back to radical notation. We're not going to worry about it. Okay, don't tell her anyway. Okay. We're going to stop right there. We'll just stop with 3/2. We'll just stop with our power notation, okay, and we're good. Now, again, you can sure check it, you know, and so forth, but it's going to work out just fine. Because remember, at the end, you kick out a 2x, but there'd be 1/2 sitting there, and 2's a cancel, and you got that. All right? Let's look at another one. Last one. Hang in there. Definite integral. What do we do when there's a definite integral? Well, the only difference is when we get done at the end, when we do our antiderivative, we won't have to put on the plus c, and we'll do our right bracket, and we'll plug in our e and our 1, and we'll subtract. But up until then, we do everything the same. So we're looking at this, and we're thinking, okay, what's our u going to be? What do you guess the u is going to be? Not x. Natural log of x. Why? Because it's on the inside. Now, right now, that's about the best thing we've got going for us is how do we pick our u? We pick what's on the inside. Now, you'll get into some maybe in the homework where there might be something else, but they'll probably tell you, or if not, you'll have questions about it. You'll come and see. Okay? But we'll get started with it here. So we get let u equal natural log x, the thing on the inside. So what's the du? 1 over x, and then the dx that we would swing around, right, from being on that other side. Oh, that's nice. Is there a 1 over x setting there? Isn't this x down here a 1 over x, right? Really? Sure enough, that's going to be a good thing when it comes to our substitution. So, when I substitute, now I'm not going to worry about these numbers right here right now. I'm just going to put empty boxes there, and I'm going to talk about that in a second. So, this piece on top, when I pull that out of there, what does that become? U cubed. Right? That becomes u cubed. And then what about this part here? Now I circle it like that. But what is that really? And don't say x dx. That's 1 over x dx, right? This thing I've circled here is a 1 over x dx, which is the same as du. And du, I always put over there. Look at that. Messy looking thing. What you'll find out about antiderivatives, the messier they are, probably the better. Because then you got a lot of stuff that will all substitute out. Okay? All right. Now, let's don't worry about these boxes right now. I'm going to tell you something here before we leave, though, what we could have done with this, because it relates to some of your homework. But now we would go ahead and, one option we would have is to go ahead and do our antiderivative right now, which is 1/4 u to the 4th. Now, normally we would put a plus c on here, right? But we're not going to because we're doing a definite integral. So we're going to do our right bracket in a minute. But, okay, let me come over here, and then let's substitute our natural log back in. So we're going to get 1/4 ln x to the 4th, and then we're going to right bracket that from 1 to e. Does that make sense? Right? When we do fundamental theorem part 2 to do a definite integral, we got to do the antiderivative. We don't care about the plus c, remember, because it's going to subtract out. So we don't put the plus c. We sub our x's back in, and now we go from 1 to e. So now we're going to plug an e in. What's ln e? 1 to to the fourth, 1 times a fourth, that's just 1/4. And then we plug a 1 in, what's ln1? 0. To the fourth is 0, times the fourth is 0, and sure enough, we just get 1/4 as an answer. Remember, if it's a definite integral, it should be just a number answer. Now, let me do something in red here that is an option. And you decide how you want to do it. But on a couple of your homework problems, they kind of ask you a question like this, so you got to know what they mean. With a definite integral, since we're going to get a number answer anyway, it doesn't matter if we go back to the starters. It doesn't matter if we go back to the x's. Now on this one it does, because on this one before, it does matter because we wanted the antiderivative of this, so we want to have x's in our final answer, not u's. But in this, our final answer is just going to be a number. So right here, I could have stopped right here and done a right bracket. The problem is, I can't put 1 and e here. Why not? Well, what kind of values are 1 and e in this problem? Think of the graph. It's the area from 1 to e. They're x values, right? 1 and e are x values. What do I need to have here? Not x values, I need u values. So I need to take this guy and turn my x values into u values. So what I would do is take an e and plug it in here. What's ln e? 1. So when x is e, what's u? A 1. And I got to take my 1 and plug it in here for x. What's ln 1? 0. I need to, so one option would have been, when I change all my x's to u's, also change these x values into u's. Now when I do my antiderivative, I could have done this. Now I plug in a 1 for u, I get 1/4. I plug in a 0 for u, I get 0, and I still get my answer 1/4. I didn't need to take that step of turning it back into x's and then using the 1 and the e. So when I substitute out, you know what I didn't do? You notice I didn't circle these, right? Well, you could treat those as a substitution also. You need to take out the x values here and turn those into u's as well. You can do it either way, you get the same answer, so I don't care. All right, on the homework page, it talks, it's got some problems listed. Now, some years I've split this up. Like after the quiz, I normally assign some problems, but last Friday I took pity and didn't give you homework, whatever. So we're gonna combine a little bit here. So it's got 3 lines of 5.4. So you do the first 2 lines for sure. So right under the quiz, it says 5.4, page 340. So it's got 2 lines, so you do those 2 lines for sure. And then the bold, it's kind of like that derivative page we had before the gateway test where we had a whole big page full of problems, and we just went through and we just practiced those and practiced those. Well, that's kind of what that next, the ones in bold are. So it says do sum of 23 through 73. All right, so we're going to continue to do that over multiple days. So for sure the first 2 lines, and then if you want to get into a few of those, that wouldn't be a bad idea. Okay.